history goes way back before that.
When does it go back to?
It goes back thousands of years.
Thousands of years. So how does that work with the flood?
Which flood? The Noah flood. We don't believe in the Noah flood.
Oh, of course. All right.
Zoroastrians don't believe in the Noah flood.
Okay, fair enough.
What do you mean?
Okay, fair enough.
Hiya, guys.
Just research Zoroastrianism.
Yeah, okay, well...
Because we've all done the biblical bullshit, we've all done that.
Enjoy
but no
it.
one actually researched Zoroastrianism where the whole history comes from. First civilization was where?
This is your story, yeah?
It's not my story, it's a history. It's not my story.
Were you there?
I'm talking about the cradle where the cradle of civilization was in Babylon. That's where it started from, near Iraq and in Iraq.
Were you there? Were you there?
I wasn't there, I'm reading from history.
Well, okay. How do you know it's true?
Because I'm reading from history, just like you're reading from history.
Okay. So,
how do you
again,
know your stuff's true?
Well, okay.
This is the thing. What I'm saying is, I know I've read about the biblical census, but you've never read about the Zoroastrian census, so you wouldn't know about that.
The what sense?
Zoroastrian.
What's that?
It's the first monotheistic religion in the world. The first religion that says there's one God. Google it. It's in
That's
Google.
what you think.
It's not what I think. It's what the researchers say. Just Google it. That's what I'm saying.
There's researchers say that the Earth is round.
All I'm saying is, can you please research it?
Or
are you not going to even research it?
There's researchers say that the Earth is
Would
round.
you research it though? This
Probably
is something
not.
to learn.
I'm not interested.
You see, this is it. I'm not interested to learn.
No.
Well done. Good luck.
Yeah. Good luck to you. Was he a friend of yours?
No, he's
Well, what was he doing here then?
What is it, you?
No, he's
Oh, I thought it was really, I thought it was your mate or something. I'm not, there is evidence that there was a flood, okay? So much so that there's like seashells found on Mount Everest. Yeah? How do seashells get onto Mount Everest, yeah? There are people talking about a mud flood, yeah? Have you heard about this? Mud flood, yeah? There's all these buildings covered in mud and all this stuff that's underneath mud. Well, they're talking about this this mud flood coming. It's actually the flood, yeah? They covered everything in silt, yeah? Very quickly, within days, yeah? Noah's Ark was found in 1980, yeah? It's exactly where the Bible says it was, yeah? The Red Sea crossing was found, Red Sea is about a mile deep everywhere, except for this one place when there's this like land bridge under there, and they found horse and human skeletons and chariots and chariot wheels down there.
I think I watched
I watched that
Yeah.
yesterday.
So Sodom and Gomorrah was found, and all these places and landmarks that the Old Testament talks about are all there. You can go and see them. Yeah. To say this guy come and say, oh, Zoroastrianism, we got a history. Well, the guy wasn't there. There isn't any physical evidence that says, okay, what you're saying is true. There's nothing tangible. Just some books. Yeah. Well, I've got books that say the Earth's round. I don't believe that. Because I can go and see evidence that it's not. Okay, that's all I'm saying. Yeah. But you get people with an agenda, and it sounds like I've got an agenda, but I came from having a different agenda. I came from atheism, utter, total, rabid atheism. Yeah, for 40 years, and then I started researching the Old Testament, and I had to change my viewpoint because it was the evidence was so compelling. Yeah. And it's not just looking back in history and looking at place names, the movements of people and that sort of thing. It's what's going on in the world today. It actually explains what's going on in the world today. Yeah? When you find out who the players are and who they are today, it all makes sense.
But don't you think that if you said that the Vatican control the religions and stuff like that, yeah?
No, I did have the bread, but
they all the Bible.
No, they didn't write the Bible. They edited it. They chose what books should be in it, but they didn't write it.
So if they chose what book should be in it, that means there's things what are missing from it then.
And that's what we're finding now. There's a set of 14 books called the Apocrypha that were in the 1611 Bible, but taken out afterwards. There are other apocryphal books that are that came out of the Dead Sea Scrolls, and they just give you more information about what's in the Old Testament. So yeah, that's it. You filming it?
Just that last 5 minutes I was.
Okay, because
nice one, man.
I'll just. Then you find stuff. There's the indoctrination right there. All these little kids looking at that, being told by their teacher they live here. This is the indoctrination. Yeah? At an age where they can't critically interpret information. This will form the basis of their reality. This is how easy it is. It really is. Even when NASA puts their stuff out that looks like this, they forget that the clouds are supposed to move. In fact, you find in the clouds they show in their pictures, they use a clone tool to use the same picture of cloud and stamp it around the globe. There's even the word sex written into the clouds somewhere, which is a known psychological trick to get you to engage with something. Every time I fly, I always take the time to speak to the pilots. And half the pilots I've spoken to have seen the curvature. Half the pilots haven't seen the curvature. According to mainstream science, nobody can see the curvature from a passenger jet.
I've looked at flight paths of things between South Africa and South America, or Australia, and it's more so going over Antarctica. Which on a globe,
Antarctica.
well, they do. There are transatlantic flights.
Oh.
Not many, but it depends on the range of the aircraft.
And really, we've been trying to find. There's none. Nothing is allowed to fly over the South Pole.
Okay, so that comes down to ETOPS ratings in terms of how far an aircraft can go from an airfield. Such as the longest one is 330 minutes. That's the A350 or something. Which pretty much puts a hole over the Antarctica because it's so far away from every other airfield.
Mm-hmm.
They can't go over that because if they have a problem, it's too far away for somewhere to land. It comes back down to the ratings. But they can go often very near it.
Well, they say that, it's too far to land in an emergency. The moon landing is absolutely fake. The supposed lunar lander. One good thing is that it's really accurate because there's no blast crater underneath the lander where there's a massive rocket engine, and there's no dust in the pads there. So, very accurate indeed. But to think that this contraption made it to 238,000 miles away and landed on the moon is just ridiculous. Can somebody tell me how a zip holds back the vacuum of space? Okay.
But sorry, I didn't quite catch how that would make gravity.
Well, let me
false.
Let me show you an experiment.
No. I mean, I think this is quite important, right?
Well, this is where I was going.
That something is weak doesn't mean it doesn't exist, right?
Okay. Right. So, a vacuum is much more powerful than gravity. We know that because Mythbusters did a show where they used a standard vacuum cleaner to lift a car. Yeah, just like the magnet lifting paper clips. Yeah, a vacuum cleaner literally lifted a car.
Climbing? Yeah.
As the crane takes up the slack.
Come on, baby. Hold on to this car.
Of space, yeah, was able to lift a car. Right, so we have a vacuum outside of this Earth, apparently, right? Which is.
But if you stop making the vacuum in this vacuum cleaner, which I think actually it might be, some sort of magnet which actually did that, but maybe I don't know. If it's vacuum, it's vacuum.
Yeah.
Maybe if you remove the vacuum, then doesn't the car go,
Yeah, as soon as they switched the vacuum cleaner off, it fell.
Right.
So the point I'm trying to make is the vacuum generated by a standard vacuum cleaner, right, was able to lift a car on the surface of the Earth, where the gravity is strongest, yeah, easily lift this car, okay? Now we have a vacuum which is many times, orders of magnitude more powerful than the vacuum generated by that vacuum cleaner, yeah? Acting on the atmosphere of this ball Earth, okay? So why isn't all the atmosphere dragged off into space? Because, you know, whenever we see a high pressure next to a lower pressure, there's movement from high to low, always, yeah? So we've got a pressurized system, the Earth, right next to an unpressurized system, space, and no movement from one to the other. Right? There's no barrier in the way, apparently, yeah? So there should be a movement. And the only thing that's supposedly stopping this movement is this weak force called gravity, which I've already just shown is overcome by just a piddly little vacuum generated by a vacuum cleaner.
I mean, this is something that you can try, right? Try yourself. Let's try. We can try on this table. We'll try on this table. Let's take a vacuum cleaner and let's try to see if we can lift it.
Well, if you see the Mythbusters
let's
thing,
just see if we. I mean, this is something that we can do, right? Is this table heavier than a car? Yes or no?
Heavier than a car?
Is this table heavier than a car? No,
it's not.
Right? So therefore, you need to have a weaker vacuum to actually lift it up, right?
Yeah. Okay.
So let's just take whatever vacuum cleaner and just actually try here.
No,
do you think that this
we could do the same with a plunger? Actually, if we get a good enough seal on the plunger, yeah, put it on there and we'll lift a table. That's a vacuum. We create a vacuum with a plunger, yeah.
Yeah.
And it sticks. If it's got good enough seal.
You said vacuum cleaner.
It doesn't matter. The vacuum cleaner. The vacuum cleaner is the source of the vacuum. Yeah?
Right.
It doesn't matter where the source of the vacuum is. Yeah. It's just a vacuum, a lack of atmosphere. Yeah. You can create one with a suction pad. Yeah.
Oh yeah.
Okay.
Definitely.
And that vacuum, that minute vacuum compared to the vacuum of space, will lift that table. Yeah. We'll even lift a car if you get a good enough seal. Yeah. That's what I'm saying. If you've got a minuscule vacuum that can overcome gravity here on the surface where gravity is supposedly strongest, yeah, why isn't it not sucking off all the blowing all the air into the vacuum, yeah, so that we should be not being able to breathe right now?
Because well, in a sense it is, right? Because the Earth gets thinner when you go higher, right? So
yeah,
there's no movement of the Earth towards the space, but like the Earth, it's not like you get a straight sort of like one time where it just becomes vacuum, right? It's like the Earth gets thinner and thinner, and then at the end it just gets nothing.
Okay, let's go with that. Okay, so let's imagine this table's the Earth, and we've got the atmosphere here, and right now there's no vacuum attached to it. So let's say it's not thin; it's the vacuum. The atmosphere is like full strength up here as well. Okay, now we apply vacuum. Right, the molecules at the top start to go off into space, yeah, because they're right next to the vacuum, yeah. So they go off, and now you've got a lower level because now this lot's been taken away, yeah. So now you're down here, okay. Now this is next to the vacuum, that gets taken away, and this is next to the vacuum, and that gets taken away, and so on all the way down until there's no air left. Because as I said, even down here, a small vacuum will overcome gravity.
Yeah. No, I mean, I don't know what is the thing. So if you want to, I don't know what is the what is the reason for this.
Well, all I'm saying is I don't understand the model, because the model does not make sense. You can't have a pressurized system next to a vacuum and hope to keep the pressurized system without having a barrier in the way.
Yeah, I don't know. I haven't thought of these questions.
Is there any
In my opinion, the Big Bang theory and the theory of evolution and the ball Earth theory are all interlinked, and they're all there to make us feel as though we're insignificant. We're small, tiny,
miniature,
unimportant, pieces of slime crawling around on a speck of dust in an infinite universe. If that's true, and there's no purpose, there's no meaning to anything, then our owners can do whatever they want with us. Then, this is all accidental, so food can be genetically modified because it's imperfect. We can be modified because we're imperfect. If we realise that this is the universe, and
complete universe.
Yes, this system is is everything. Everything that NASA has put out is CGI, is fake. Okay, people say, I think you mentioned it. If you look out into the universe, you see that the moon is round, spherical, and the planets are spherical, and so why are we flat? Well, how do you know that the planets and the stars are spherical? All you get is, if you look for a telescope, you see a flat disk. If you think you see a spherical shape there, well, it needs two eyes to resolve 3D. If you're looking for a telescope, you can't see anything in 3D. It's going to be flat anyway. So all you see is a flat blob of light. It's only NASA that's given you these beautiful pictures of so-called planets and stars. Yeah. So it's a fallacy to say, well, everything else out there is spherical, so we must be. How this is special. So why? It's like saying a basketball is round, so why isn't the court round? It's a fallacy. So this idea of a ball Earth, theory of evolution, the Big Bang, is all about making us feel nothing, so that we can be used. If everybody realised how special we all are, how unique every single life is, then this whole world would change overnight. We wouldn't allow ourselves to be used by this cabal. We wouldn't allow this planet to be destroyed, because they're destroying it because, it's just an accidental planet, one of millions. We've found other Earths. Eventually, if this one gets too messed up, we'll go to another one. No, this is it. So if we all realise that, then we wouldn't allow all these things that are going on.
The question is, if the Earth is flat, could you please explain why everything else within our solar system is not flat? Well, that's what I asked.
The question I'd ask anybody asking that is, how do you know that those things are spherical?
I didn't say they were spherical. I haven't given them a shape.
Okay.
I'm just saying, if we live on a flat Earth, fine. Can you please explain why all the other stuff is not flat?
All those things that we see in the night sky,
yes,
are just points of light.
Okay.
Yeah? When you actually zoom in on them with a camera such as this, with a high zoom, you can actually zoom in on them, which is a bit suspicious because they're supposed to be 2 quadrillion miles away.
Yeah.
With an 83 times zoom, there should be no difference. Yeah. So literally, when you zoom in on these stars and planets, they're not, perfectly circular objects. Yeah, they're actually all unique. I don't know, things. I mean, one looks like watery fire, another one looks like electrical discharge, another one looks like an amoeba, another one looks like wheels within wheels. They're.
So then we are in agreement that the Earth is flat, but all the other things are not flat. They have their own different shapes, which you've given. Oh, we don't know.
We don't know.
Oh,
they're just lights. As far as we can tell, they're just lights.
But how do you know they're lights? What led you? No, I mean, what led you to the 100% belief that they're not an object, but it is light? Like, for instance, if I'm asking as a 7-year-old, if the moon comes up, and I look up at the moon, and if I even zoom into the moon, I can see craters on the moon.
Indeed.
I can't see through the moon.
Indeed.
So that object does not look flat to me.
Well, here's the thing. If it's a body, a spherical body,
Yes.
which is reflecting the sun's light, well, it's not reflecting like any other spherical body, because a spherical body reflecting the sun's light would have a hot spot. No matter how matte the surface is, there'd be a hot spot exactly where the sunlight strikes it directly, and then the light would drop off around the curve. Yeah, we don't see that. We see the moon lit up uniformly over its whole surface. Yeah, it's either not spherical or it's emitting its own light. And it turns out that the light emitted out from the moon is completely different from that of the sun.
It's separate from the sun.
It's a cooling light.
Measured.
Yeah.
Yeah, I've heard that, but what shape is it?
Well, again, it looks at least hemispherical.
Define hemispherical. I've never heard that word before.
Half a sphere.
Half a sphere.
Yeah, because we can only see one side.
Okay.
We can only ever see one side. Yeah.
Yes.
Which doesn't make sense because, you know, so many times the Earth has had a huge earthquake, and they say, well, it slowed the Earth's rotation by this much, you know, and I've done that several times. Yeah. So this rotation of the moon is so precisely timed, so that it always faces the same way. Yeah. If the Earth slows down a little bit, then that's going to throw that out.
But what you believe, and correct me if I'm wrong, the Earth being flat, it doesn't rotate. It's stationary.
It stays stationary.
So all the other things within the solar system, do they move or are they stationary?
They're moving all together.
They're moving around the flat Earth, or underneath the flat Earth, or
there's a firmament, there's a dome, and according to the Old Testament, the stars are in the firmament.
Okay.
Yes. And
so you have the flat
sun,
Earth, and then you have the dome above the flat Earth.
Yes.
And
Now,
so within that, they all rotate within that dome.
Yes. The stars are supposedly in the firmament.
Okay.
Yeah. And the firmament rotates and the stars rotate with that.
All right.
And there are things we call planets.
Yes.
The word planet means wandering star.
Yeah, I've heard that from.
So these are the same sort of things as stars, but they're moving on a different trajectory.
Okay, I see.
Apparently close to the Earth, because those wandering stars are also known as the Watcher class angels.
The Watchers.
Yeah, the Watchers. So they were close to watch over the Earth.
Which is another name for Nephilim.
Exactly. That's why all the planets are named after Nephilim.
The Nephilims are supposed to be beings.
In Greek.
What, in the Book of Enoch you're talking about?
Sorry? No. They're named after Nephilim because the fallen angels and Nephilim, they were the heroes and heroes of old.
Yes, so why would you then call planets Nephilims if they're beings, as you've described their beings?
The ancient word hero doesn't mean the same as it means now.
Okay, okay.
So they were the giants and the titans and all that. So the names of them, right, were translated in various different languages. So we use the Greek names, the Greek and Roman names for the planets.
So just to be sure what you're saying, Earth is flat. There's a dome above the flat Earth, and within that dome we have the plethora of stars and the other planets, which have different shapes. None of them are spherical, different shapes, and they all rotate around the flat Earth, or they just rotate above the flat Earth?
The firmament,
What does the firmament mean?
The firmament is the dome.
The dome?
Above you, anything above.
Okay, so they're above the Earth, rotating above the Earth.
And inside the dome is the moon and the sun.
The moon and the sun.
They're separate entities. You know, again, the Book of Remembrance says they were created as great luminaries. Okay.
Anytime your spirit transcends, right, and it goes up, or even down, believe it or not, you're in the atmospheric. You're in a different realm.
But I hear that more from a religious perspective, though. When I hear that,
well, I'm not a religious person.
You say that, but a lot of what you say does.
I know, but there's a difference. Yeah.
Okay.
The Old Testament is a book of history, real history, law, and guidance. Yeah, for one particular people. Okay. What's happened is other cultures have come along put their book on top of our book, okay, and created a religion around it. We don't belong to a religion. We belong to a way of life.
Okay.
That's what the Old Testament describes, a way of life.
Finally, to believe the Earth is flat, can you explain then why doesn't water come off the edges? Is something holding the water in?
If you look at the model of the flat Earth, imagine a dinner plate.
Yeah.
Okay, and the North Pole's in the middle. The continents are strung out round the North Pole.
All right.
And around the edge is what we call Antarctica.
Okay.
It's a 200-foot ice wall, followed by 300 miles of plain, followed by 2-mile-high mountains, the Rockefeller Mountains, which believe. So that's what's keeping the water in.
All right. Can we ever travel to those mountains?
No, because if you try, you get turned away by the military.
Can I ask you a question based on that? Do you think there's anything over the mountains?
Well, I believe, going by what Admiral Byrd said, and this map that was in a newspaper 100 years ago, apparently it's a 1,000-year-old map. There are more continents beyond the ice. And Admiral Byrd said that he found a continent the size of the continental US that's uninhabited on the other side of their base.
But it hasn't been proven yet.
That's what he said. But there's video. There's actual footage of them, going across Antarctica and finding warm water lakes.
Admiral Byrd, footage of him.
Yes.
We're going way back to the 1950s. There's footage of that.
Yes.
Okay, I'll go looking for it. Admiral Byrd.
Warm water lakes, and they're walking around in t-shirts and stuff. Yes.
Wow. Have you guys got a leaflet or anything like that?
A what?
Leaflet? Any leaflets?
The leaflets are handing out. Can I put one of the leaflets here now?
Nice one. Thank you very much.
Well, yeah, thanks very much for your information. It's been very helpful. Thank you. Goodbye.
So, you've got like the computer-based altitude indicator. This is a mechanical one, yeah?
They're all more or less of the same thing, but slightly different supplies.
Okay. Do you ever find you have to adjust them in mid-flight at all at any time, or recalibrate them?
No.
Okay.
Normally pretty good. These are obviously less accurate, but these are pretty good. And they come off lots of different sources, so they're very good.
Okay, because that one, I've been looking into that. That one's completely mechanical. You spin it up and it's a gyro. Sorry?
That's our backup one if you need it.
Yeah. Okay. Another question. Sorry to ask all these questions, but okay, when you let go of the yoke, right, and you trimmed for straight and level flight. Okay.
This is auto trimming.
Well, yeah, I suppose it's auto trim. Everything's automatic now, isn't it?
So we cheat.
So you let go of the yoke and it auto trims. Now that's straight and level flight because of the air flying over the control surfaces, yeah?
Yeah.
It's not reference to the ground at all anyway. No. It's literally the control surfaces.
Well, it's reference to that. It will look at the attitude indicator and it will sort of go like 0 VS.
Yeah, so it will say if you start climbing, it will like correct.
Yeah.
So you're going literally
to a certain extent, yeah.
You're going literally a straight line.
Yeah, but it's slightly nose up.
Slightly nose up.
It depends how the aircraft's designed.
Okay.
Because the wings are set at a certain angle and a certain speed. If you go faster, then the nose will go down very slightly to hold level.
Okay.
If you slow up, the nose goes up to hold level.
Oh, sure, yeah.
Do you have a flight sim at home?
Yes.
Okay. I see why all the questions.
Well, so how do you correct for the curvature of the Earth? How do you nose down for that?
Well, you don't have to, because you're flying along in an air block, if you like.
Right.
That is constant pressure going. Well, not constant pressure necessarily, but the air block is all the way around the Earth.
Well, this is why I'm stuck because you're going in a straight line, and that's because of the air flying over the surfaces, yeah. But so there's no reference to the ground. So this really confused me. Why are we going in? We're going in a straight line. The Earth is curving away under it.
But you're really flying in the block of air.
I understand that. Yeah.
Stuck to the Earth.
But the air, the air's not. The air's the air.
You know,
it doesn't matter what the block is.
It's not saying, but it's gravity to a certain extent, isn't it? You know, so you're sort of going along, and if there was no gravity, you'd go in a straight line forever.
Okay, but gravity's, well, as you're going like that, the gravity's now pointing the other.
So every time you go along, it pulls you down a bit.
Okay, that's what's really confusing. Anyway, sorry to.
No, don't worry.
Sorry to stop you.
Are you disembarking here?
Yes, I'm going to have to go. Yeah.
Oh, you go. Okay, good.
Thank you very much. Sorry to
No,
bother
no,
you.
not at all.
All right.
No,
cheers. All right.
Sorry, I just need to do.
I mean, this is kind of what I wanted to say, really, because you know, you're saying the lack of curvature, right? Okay, let's say you cannot see. You're talking about this, you know. What I'm assuming is like you put something which is of known height, and then you go somewhere far, and then you try to see whether you can see this one with spectacles or something. Is that?
Yeah. It's not so much the known height, but you know, see the bottom of it. For instance.
See the bottom of it.
Yeah.
Right. Well, I mean, you know, at which height do you do your observations? At, you know, how is the sun reflecting? All this sort of thing matter, and you just have to have it. Like you have to go. You know, this is not about. You're not trying to measure the actual radius of curvature, right? You're trying to measure whether the Earth is round or not. It's a different problem. Right, so if at any point you go further enough and then you don't see the stick anymore, then the Earth is round. Is that?
Well, absolutely not, because you know you can do an experiment yourself. Get a camera, place it on the ground, yeah, and on a flat surface like a basketball court or something, yeah. Walk away from that camera, and you'll find that your legs disappear, and you know, up to your knees will disappear.
No, but I mean.
That's just, no. This is how, you know, perspective works on a flat surface. Yeah.
Right.
You know, we're told this is the 500-year-old proof of the flat Earth.
So on a football ground, for example.
Mm-hmm.
So I mean, all right. Okay. If this is different. Okay, misconception then. The curvature of a circle or a sphere, when you take a big radius, tends to be flat, right? That's what it is, right? But it's not flat. So it's kind of like measuring the curvature of a marble and measuring the curvature of a big, whatever, helium balloon or something. Then, you know, you will find it like much smaller, right?
Like an ant on a beach ball or something.
Exactly. So at this distance, you know, especially of a football ground, or you know, that is just not relevant. You can't measure because the displacement would be like much smaller.
That's not what I'm saying about that. No, I'm saying that this idea that, you know, as something goes away from you, it will go over a curve, yeah, because you lose the bottom of it, yeah. No, on a flat surface, yeah, you can actually repeatably demonstrate how just walking away on a flat surface, it appears as though somebody is disappearing below a curve, yeah, but they're not. Obviously, they're on a flat surface. Yeah, I've done a couple of videos that show that effect. Yeah.
So I mean, right. Let's. We're next to Brighton, so I guess I have to say that. If we all go to the I-360 and then climb on top of the, take the big ride and go on top of it, why can't we see the Eiffel Tower?
Because we can only see a certain distance. We've got atmospheric effects that mean you can't see. If you live in California.
No, but okay, let's just say.
Let me just give you an example. If you live in California, you get the weather report in the morning. You get as along with the weather report visibility, 10 miles. Yeah, it's not because of curvature or anything. It's because the atmospherics limit the distance you can actually see.
Yeah, but you could design some experiment where you have a laser and you shine it from the Eiffel Tower, and you could have telecommunication like this. Boom, you don't need to have satellites.
Well, you don't need to have satellites because, again, we have line of sight communications, which, again, should be hidden by the curvature. Yeah, there was an experiment.
Yeah, so satellites do exist, right?
No. We have line of sight experiments with. There was an experiment in. There's a horrible video, a horrible documentary, but they used. I think it's called the convex Earth, and they got scientists from South America. They did an experiment where they were sending a Wi-Fi signal over a distance. I think it was 50 miles. Where it should have been hidden. Now this Wi-Fi signal is line of sight. Yeah, if it's blocked by anything, you won't get. You won't get the signal.
Where did the Wi-Fi signal go?
Sorry, they were beaming a Wi-Fi signal from one station to another. There's a frog down there. Beaming a Wi-Fi signal from one station to another one 50 miles away. Right, the curvature should have blocked that signal. It's Wi-Fi, line of sight. Yeah.
Well, it depends on which height did this.
Radio. It's radio. It's line of sight. It can't go through the Earth. Yeah?
No, but it depends on which height you.
Well, no, they were doing
broadcast.
Right? The height is taken into account. You can go online and get the Earth curvature calculation. One of the parameters you have to put in is your eye height. Yeah. So it's taken into account. Okay. I've got pictures of the White Cliffs of Dover from Calais or Boulogne. I can't remember. Boulogne, I think it is. Yeah, it's 31 miles away from the White Cliffs of Dover. Yeah, the eye height is 30 feet. Yeah, that's where the picture was taken. And with the Earth calculator,
the cliffs are way higher than that.
I know. But with when you
can you see the base of the cliffs?
When you plug those figures in, yeah, it should be 353 feet should be hidden. Yeah. The cliffs are 350 feet, yeah, and yet from that picture you can see the base of the cliffs. You can see all of the cliffs, yeah. What I'm saying, I'm not making stuff up here. Any of us can go out and do our own experiments, yeah. Plug in the figures into the calculation and see, no, I'm not supposed to be able to see that, but I can see it. There it is.
I think this is a different problem, right? There is one question is whether the Earth is round or not. The other is what is its actual radius. All right, I think I can.
Maybe Dave, I was over to you, and I was just going to ask you maybe what's some of the sort of the leading points in your mind why you think obviously the Earth is flat.
Okay, leading points. Well, the first most obvious is the complete lack of curvature. No matter how much we try and find the pesky curvature, we can't find it. As I said, I mentioned the curvature calculation, which on a 25,000 mile circumference should be 8 inches per mile squared. That's the amount of drop that you should experience. So armed with that calculation, you can go out and if you have a landmark a known distance away, preferably over the sea, because obviously there's nothing in the way, you can do sighting experiments to see how much you're supposed to be able to see. And I guarantee you'll see much more than you're supposed to be able to see. So between that and the gyroscope, that's my pet one. The gyroscope has a property called rigidity in space. That means once it's set spinning, it will stay in its orientation no matter what you do with it, regardless of gravity, regardless of where it is on Earth. It will stay in its original orientation, according to space. So you get aircraft have a gyroscope. They always have a mechanical backup gyroscope in their artificial horizon. So how it works, very, very simply, is before the plane takes off, they're on a level surface. They spin it up so it gives you the true reference to the ground. So once that reference to the ground is set, then they always know where the horizon is, even through thick cloud. It's not because, as the plane sort of does its manoeuvres, the gyroscope will stay in its original orientation. Fundamental principle of gyroscopics. If a plane is doing, let's say, 4,000 mile trip, I think that's something like 90 degrees. Maybe it might be, I can't remember, but it's probably about 90 degrees, or 60 degrees, I think it is, of arc that it will make over the round Earth. So the artificial horizon should start to roll backwards during straight and level flight, but it doesn't. It tells you that a plane is flying over a plane. Now, people have said that gyroscopes have these things called pendulous vanes, which correct for the curvature. But when you actually look into what these pendulous vanes are there for, it's to stop the other property of a gyroscope, which is called precession. And precession can be induced mechanically by sort of, if it's a vacuum system, by uneven air or particles of dirt in the air, or it can be induced if you do too many manoeuvres. You get to a point where the gyroscope starts tumbling. So they invented these pendulous vanes to stop it tumbling. It doesn't correct for curvature. So that's it. It's those two. I think I've got to add as well, while I'm on that subject of planes, is that planes, its attitude, an attitude of a plane, and straight and level flight, is determined by the air flowing over the wings. Nothing to do with gravity, nothing to do with the surface of the Earth. If the air is flowing in the right way over the wings, the plane will fly straight and level. If you let go of the yoke of the controls, the plane's supposed to fly straight and level, but sometimes it doesn't. So they have a thing called a trim wheel. So they trim the the control surfaces so that the plane will fly straight. Okay, so if a plane is flying straight and level over a curved surface, it will start to gain altitude, and the pilot would have to nose that plane down to keep it straight and level. But no pilot ever has to make changes. They never have to nose down, and the plane will not automatically follow the curve of the Earth. It will fly straight and level according to the airflow. Right, you mentioned detecting gravity waves.
Just before you continue, so Cardiff has a gravitational waves department. They get very angry if you call them gravity waves. Gravity waves happen on water, these are gravitational waves. I don't know the difference, but they get very bent out of shape.
The thing is, before I was into the flat Earth and everything, I was really well into science, really into quantum physics, Einstein's theory of relativity, the whole works. So when LIGO, was it LIGO? LIGO, sorry, yeah. When they first started doing their experiments, I wrote to ask a physicist, and I I asked them a question and they weren't able to answer. Well, they refused to answer. Okay. I've asked the same question over the years to various people. None of them answered me. Okay. So this might get a little technical, just a little bit. Right. So the way LIGO works is that it's kind of like an L shape. Okay, with these 15-mile long legs. And what they do is they fire a laser, split the laser into 2 directions. Okay, bounce them back off a mirror, recombine them, and you get an image on a screen. Okay. Now, if at any time the distance between the 2 legs changes, so if a gravitational wave goes along one side, it will change the distance, change the size of that leg. Okay, then there should be an interference pattern on the screen.
Yep.
You agree?
Yep.
Right. So this is supposed to prove Einstein, but what Einstein said is that it's not the gravitational wave isn't in space; it's in space-time. So if space contracts, then time slows down so that the speed of light stays the same. So if you're doing an experiment with the speed of light, you will never detect gravity waves, because if the gravitational waves, so that if one leg shrinks slightly because of this gravitational wave, then time would slow down for that beam of light. So it will arrive exactly the same time as the other beam of light. No interference pattern. So if they detected something, that means Einstein was wrong. So if they don't detect something, that also means Einstein was wrong. So what do you got to say about that?
So
leave it there.
Yeah.
That's the best answer today.
This would absolutely be the case if you were doing this experiment with anything other than laser light, or light in general. Whatever speed you're travelling at, if you were travelling at half the speed of light and you fired a laser, you would see that laser go away from you at the speed of light. Yeah. So it doesn't actually matter about the fact that the light is slowing down because it's still travelling at the speed of light.
Don't try and blind us with bullshit. The point is, you're using it. Well, Einstein says that it's not just space, it's space-time. You know, you change the space, time changes, so that the speed of light remains the same. That's the core of Einstein's relativity. Mm-hmm. So that means it can never detect a gravitational wave.
But the light is still travelling at the same speed.
Only because time is reciprocal to space. So it has to, according to Einstein, that's what has to happen. That's Einstein. It's Einstein. You don't argue with that. It's not me. It's Einstein.
It's not quite one over the other.
It is. That's it.
It is Einstein's theory. I'm afraid so. It's described it accurately.
Okay.
Go and read it, and we'll see you next year.
The beam of light is travelling further.
Sorry, say again?
The beam of light is travelling a different distance.
No, because again, it's space-time. Time and space curving, changing shape, contracting. But the speed of light has to stay the same in Einstein's theory. So, it works the same way in LIGO that it does apparently with the Earth.
Yeah.
Yeah. Yeah. Come on.
These guys have got to go. Chris is actually on a schedule.
We're tired.
So. Okay, I'm going to move on to question 2. Yeah. If gravity is the only thing holding the air to the surface of the Earth against the tendency of a high-pressure system to escape to a low or negative pressure, then when air is heated and so is less affected by a gravitational pull, shouldn't it then succumb to the force exerted towards a region of negative pressure? What?
So basically, you're asking why air can be heated and escaped, basically. Yeah? There's two competing forces. there's gravity pushing downwards, and then there's a thermal pressure of air pushing upwards. The laws of gravity dictate that the air pressure is going to be higher at the nearer the Earth than outside. So if you got a heated column of air that would rise away from the Earth, as it would rise, it will become less dense as it's less affected by the gravity, as it will be at a greater distance, and thus have a lower thermal pressure pushing upwards. So that system stays in that equilibrium state. And that's called the hydrostatic equilibrium, and you can read a lot about it.
Okay, let me get this right. Okay, so we've got a state of equilibrium.
Yeah, gravity pushing down, thermal air pressure pushing upwards.
Well, when you say thermal air pressure, what I'm seeing is you've got a vacuum next to a pressurized system. Okay? And we always see, hang on, we always see where there's high pressure next to low pressure or zero pressure, a movement from between one and the other, okay? We can do an experiment. If we had a container and we evacuated that container less than the vacuum of space, yeah, and we pierced the bottom of the container, what would happen?
Air will rush in to balance that out, basically.
And it'll fill it up and balance it out?
Yeah, it'll equalise locally, basically.
So how can, on the surface where it's the gravity strongest with a vacuum that's weaker than space, how can it work down there
because
and not work up there?
It's unfortunately not analogous, because it's not a really high pressure system against a really low pressure system. It's a gradient. So as it's really dense at the surface, and then that density decreases and decreases towards the vacuum of space. So it's not. There's no wall at which there's vacuum.
But there has to be a boundary condition, right? The few air molecules at the top will immediately go out to space, right? They'll immediately.
It's not a negative pressure system. It's an incredibly low pressure system.
We always see high pressure goes to low.
Yeah, unless there's forces acting on it, and that is gravity that's acting on it, keeping it
what I'm saying
on
is,
Earth.
as soon as the air gets heated at the top, it rises
and becomes less dense, then has less thermal pressure. So.
Oh, okay. So
that equilibrium state balances it wherever it is, and brings it back into that equilibrium. That's why we don't want it losing atmosphere.
So where can we see an example of this idea of thermal pressure demonstrated on Earth?
I can give an example right now.